We left off with the reaction catalyzed by phosphofructokinase. By the way, that's an enzyme we sometimes call PFK. It's very popularly known as that. It's just much easier to say it that way. And like all kinases, we're seeing a transfer of phosphate from ATP to some other molecule. And as with the first reaction, the phosphoanhydride breaking drives the transfer and the formation of the new linkage. Now you got to understand what we've done essentially at this point is taken a sugar and we've tacked a phosphate on one end and then on the other. And so we have this bisphosphate, which again, that means two phosphates attached. Here's an interesting question, a little blast from the past. Where's the anomeric carbon of this fructose 1,6 bisphosphate? And can this molecule linearize? Can it mutarotate? The answer is absolutely it can. Here's the anomeric carbon. There's the anomeric alcohol. It's free, and that means this sugar can still linearize. And the reason I ask that is because that's what happens next. When we take fructose 1,6 bisphosphate, at this point, we are going to split it into a linear form, and it is now the Fischer structure of fructose with a phosphate on the first position and on the sixth position. That's important because we are now going to take it and split it into two 3-carbon molecules. We go from 6 carbons to two 3-carbon molecules. As you can see, the break is going to happen on a carbon-carbon bond between carbon 3 and carbon 4. Now, we haven't done that before, but it is something that happens. I'm going to go ahead and make that a double directional arrow because this is a completely reversible reaction. Now, what do we need to say about this? Well, first of all, this is a new type of reaction. When you break carbon-carbon bond, do you remember which of the 4 reactions we said that was? Well, I'll tell you. It's a lytic reaction. Lytic means break. And because this is not using water, it's not a hydrolytic cleavage, but just a lytic cleavage. That's the first thing we need to say. The second thing we need to say is that we end up with these two 3-carbon molecules, and we've actually seen these before. This on the bottom is called glyceraldehyde. I'll put it over here. And it's 3-phosphate. Glyceraldehyde 3-phosphate, or GAP sometimes, or G3P sometimes. And this molecule is a simple triose sugar. It's an aldose, and it has a phosphoester right there. It's the same phosphoester we just put on earlier with the hexokinase right there. So that's a smaller sugar, and the other molecule, the other product, is also a sugar, and it is also a phosphorylated sugar. This molecule we call, this one's a long one, dihydroxy acetone phosphate. Here's a little question for you. After we note that this is also a PE, that's the one we just put on there in reaction 3, let me ask you a question or two. What's the relationship between dihydroxyacetone phosphate and GAP? The second question I'd like to ask you is, why do we need to have a 3 down here, but we don't need to say 1-phosphate or 3-phosphate here? See if you can pause and think about those two questions a little bit. Okay, what I'd like to point out to you is that, first of all, dihydroxyacetone phosphate, which, by the way, we sometimes just refer to as DHAP, that is an isomer of glyceraldehyde 3-phosphate. Which kind of isomer? Well, it might be hard to see because these are turned upside down compared to each other. But the fact is these are aldo-ketoisomers of each other. And maybe that's worth a note. We break carbon-carbon bond between 3 and 4. And we form 2 3-carbon sugars. And those 2 3-carbon sugars are isomers of each other. That's going to play an important role going forward. The other question I had for you is, why are these differently named? This requires a 3-phosphate and this one doesn't. The reason is because dihydroxyacetone is a symmetrical molecule. So if we put it here, it would be 1-phosphate, and if we put it down here, it would be the same thing. It would just be upside down, and it would be 1-phosphate as well. Here, we can have 3-phosphate, or we could have 2-phosphate. So you have to distinguish those. It's just a little naming issue I thought you should be aware of. All that we need to do to finish this reaction is put in that we are still at -2. We've invested 2 ATPs, but we haven't gained any back. Let's move on to the next reaction, which is, fortunately, one that's pretty simple for us. The next one is triose phosphate isomerase. For some reason, this is called, in abbreviation, TIM. I have no idea. It doesn't seem to fit. But anyways, that's what its abbreviation is. And what we're going to do is we're going to take the DHAP, we're going to do an aldo-keto isomerization on it, pause for a moment, and draw in the structure of DHAP after we've done an aldo-keto isomerization, and then give the name of that molecule. Okay, what happens when you do an aldo-keto isomerization, or actually more properly, a keto-aldo isomerization? You're going to move the ketone down to carbon at the bottom, and you form an aldehyde. And the alcohol is moved up from the last carbon to the second carbon. And do you recognize, I hope you were primed by this from the previous discussion, but we create another molecule of GAP. That is a critical issue for us. We have taken 2 different molecules, DHAP and GAP, and we've changed the DHAP into a second molecule of GAP. So we now have 2 identical 3-carbon sugars. What do we need to know about this one? Well, it's an isomerization. And we've already told you that it is an aldo-keto isomerization, or a keto-aldo isomerization. It's double directional, so we can call it either one. And lastly, no loss or gain of ATP. That brings us to the end of our first 5 reactions. Let's review. We've done the energy investment that we talked about, and we've also split our 6-carbon molecule into 2 3-carbon molecules. We'll review the overview of that on the next video.